Go.
Hello, my dear students, and welcome back to my kitchen for some more kitchen chemistry here in Grady, Arkansas. I sure miss you all, and I've enjoyed seeing some of you about town at your various jobs where you've been working, and I also have enjoyed hearing from you. Some of you have already handed this homework in. It's due tomorrow at noon. However, I wanted to go over how to work these problems. And if you hand it in late after the afternoon, please still hand it in. Only about a fourth of you have handed it in so far anyway. But if you don't hand it in before the deadline, I'm going to take up 10 points. So hopefully you'll all make a 90 instead of 100. That being said, this next part gets a little complicated. I don't have my mole box and some of my toys with me that I normally have in the classroom. But there are 4 problems in this next section, 10.2, where we explore mass volume, mole mass, and mole volume relationships. And the main thing you have to remember is any gas, I don't care what gas it is, carbon monoxide, carbon dioxide, water gas, oxygen gas, nitrogen, any gas, and this is what's really cool about moles, occupies 1 mole of any gas, no matter what it weighs, no matter anything else, occupies the same volume as every other gas. And that volume is 22.4 liters. It's a box about this big. You may have seen those white boxes on top of the goggles sterilizer in the classroom. Those white boxes are a volume 22.4 liters. And it's a good size shipping box, but not that big. And so, that makes it possible for us to do all kinds of neat determinations, like the calculations in these examples. So, let me go up here and answer section 10.2, questions 15 through 18. So, question 15 asks, what's the density of N2O, dinitrogen monoxide, a common, fairly common gas that we see, that you know as nitrous oxide from the dentist's office. It says, what's the density? And it didn't give you any values or anything to know. But here's the deal. We know 1 mole is 6.022 times 10 to the 23rd molecules. And we also know, thanks to Avogadro, that 1 liter, abbreviated L, capital L, 1 liter of any gas, I'm sorry, not 1 liter, 1 mole, abbreviated MOL, of any gas is equal to 22.4 liters, abbreviated L. So that's all we need. So this N2O, all we need to know is how much a mole weighs. So it's got nitrogen is 14 grams per mole, 14.007. But can we just call it 14 grams per mole? And oxygen is equal to 16 grams per mole. Actually 16.0. If you look at your periodic table, it'll say 15.999 and some more numbers after that. But that's 16.0. But there's 2 of them. So, I'm sorry, not the oxygen. There's 2 nitrogens. So, for the nitrogen, every mole of this dinitrogen monoxide, trivially known as nitrous oxide, I have 28 grams per mole of the N2O. 28 grams of nitrogen per mole of N2O. And for oxygen, I have 16 grams per mole. So my total molar mass of this is 44 grams per mole. So, and we also know that, thanks to Avogadro, that 1 mole of any gas is, 22.4 liters. Or there's 22.4 liters. If I want to phrase it the same way as I did the mass, it's 22.4 liters per 1 mole of any gas. So, how do I find the density? A long time ago we did some density problems, and we, for example, used the density of aluminum to calculate the thickness of aluminum. Remember that lab way back at the beginning? So density is equal to mass divided by volume. Okay? And so we know our molar mass. Our mass is equal to 44 grams per mole. And our volume is 22.4 liters per 1 mole. Okay? And the moles cancel. And what I'm going to end up with is grams per liter, 44 divided by 22.4, 44 grams divided by 22.4 liters. And when you calculate that out, you get, I did the math wrong here, or did I? N2O, no, I did it right. When I do the math on that, and I haven't done it yet, that's the only problem, I get 44 divided by 22.4, I get 1.96 grams per liter for my density. Okay, very dense gas. So much denser than a lot of them. So, let's do our next one. Question 16. That's about as hard as you can get, but that's pretty hard. But let's do them quickly. It says, what's the mass of 2 moles of sodium chloride? And sodium chloride is NaCl, and the molecular mass or molar mass of sodium, I'm just looking up on my Flynn periodic table of the elements, and I look for my mass, and I see that the mass of sodium, actually I didn't look there because I don't have one here, I looked in the inside cover of your book, and those numbers might be a little different because they were, every year the numbers change a little bit as they perfect them and get more precise measurements. So sodium, though, that I looked up is going to be very close. They only change in like the 2nd, 3rd, and 4th place and beyond. 22.990 grams per mole, and chlorine is equal to 35.453 grams per mole. To calculate the molecular mass of a compound, all you do is add the masses of the individual elements in the compound. And when I put this together, I get 58.44 grams per mole. Now it says, what's the mass of 2 moles? So I have 58.44 grams per mole times 2 moles. Moles cancel. And my mass is 2 times 58.44, or 116.89 grams. And that's your answer. See how I did that? They want to know how much 2 moles weigh. I know how much 1 mole weighs, because I can add up the masses of the individual atoms in that compound. And that compound has a formula mass or formula weight of 58.44 grams per mole of formula weight. So, the next one says, how many moles are there in 16 grams of oxygen? So question 17 asks me, I have O2, oxygen is equal to 15.999 something, and if you simplify that, you will find it's 16.0 grams per mole, but I am dealing with molecular oxygen. It's group 6. It has 6 electrons. It wants to have 8, right? And so it shares 2 pair with another oxygen, so that each of them that had 6 before now has 8. And so we form O2, molecular oxygen, atmospheric oxygen, the form we breathe. And it has a molar mass of 32 grams per mole. Okay? Now, it said how many moles are in 16 grams. So, I have 16 grams times, I want to get rid of grams and convert it to moles, so I'm going to multiply by 1. This is 32 grams per 1 mole, but it's also 1 mole per 32 grams. Now my grams cancel, and I have 16 divided by 32. Mole is my units remaining, 16 times 1, but that's understood. So my answer is equal to 16 divided by 32 is 0.5 mole. Okay? And then the next question kinds of extends this. It says in number 18, what is the volume of 16 grams of O2, 16 grams of O2 at standard temperature and pressure? Okay, let me tell you what STP means, because when I say 1 mole of any gas equals 22.4 liters, that's only true at standard temperature and pressure. The standard temperature is 0 degrees, and the standard pressure is at sea level. Okay, so we're a little bit above sea level, and we're hopefully not working at 0 degrees. But that's my standard temperature and pressure. There's another one, prime, where it's at 25 or 20 degrees or 22 degrees, cool room temperature. But this is standard temperature and pressure. And so I know I have 16 grams, but from the previous problem 17, I know that 16 grams is equal to 0.5 mole. Okay? And I know that there are, I'm going to multiply it by 1, 22.4 liters per mole. Now, moles will cancel. There's my dimensional analysis. 22.4 liters per 1 mole of gas, any gas, and multiply that by 0.5 and you get 11.2 liters. Because you have half a mole, you'll have half that volume. I'll work section 10.3 in the next video. I'll have it up this weekend. Technically Friday is Good Friday, and Monday is something called Easter Monday, the day after Easter. I hope you celebrate Easter well, but safely, and that you stay safe. Tomorrow or the next day I'll go ahead and post that answer to 11.3 and work those problems on percent composition for you.